going to talk, we're going to review basically all of the things that we discussed on Thursday, except we're going to add just a little twist to it. But again, we're talking about, we introduced the first law. We said that the internal energy was a state function, and for state functions, the path that you move between one state and another doesn't matter. The total difference between the two states is the same no matter what path you take. And we looked at a hill, and we said that height is a state function. No matter what path you take from one side of that hill to the other, your change in altitude is the same. And so the fact that internal energy is a state function means that the difference in energy between any two states is always the same no matter what path you take to get there. And mathematically, one of the consequences of being a state function, of something being a state function, is that it has what's called an exact differential. And what that looks like is if we have a function of x and y, then and we want to express a change, a differential change in that function, that we can break that differential change up into a sum of changes with respect to each variable. So we can take the partial of the function with respect to x and multiply it by whatever differential change in x, and then we can add to that partial of the function with respect to y and multiply that by the differential change in y that we move, and that sum will always be equal to the total change in that variable. Right? So state functions have exact differentials. The fact that that's true allows us to do some mathematical manipulations on energy functions that express any change as the sum of changes with respect to the different components that describe that function. So internal energy is a state function. We're going to be introducing enthalpy in a moment, and then enthalpy is also, it turns out, a state function. And we'll perform some mathematical manipulations on the internal energy and the enthalpy that will hopefully kind of describe to us or help us to understand what components contribute to those quantities. So just real quick review. Internal energy, the first law of thermodynamics tells us that energy can't be created or destroyed. It has to come from somewhere. And so as a consequence of that, we have that any change in energy in the system is equal to the negative change in the surroundings. And internal energy is a state function, so total change is difference between the final state and the initial state. And we're kind of learning to think of any change in energy that happens with the system as being a function of these two quantities, heat and work. And we talked about those a little bit, but I didn't explain them quite as clearly as I was hoping to, so I'll try another shot at that today. There's two kinds of work. There's work that is done against conservative forces, and there's work that's done against non-conservative forces. And so, again, work is the measure of the force times the differential distance that you move against that force. So if we have something that's pushing us down, like gravity, and we want to move against gravity, we have to exert energy to push a mass against gravity. And if we have a charge, we have to push with energy to move against that charge, or to move against the forces of attraction between charges. Friction is also a force. If we have friction holding us down, we have to push with some force to move against friction. Friction is a non-conservative force. Any energy that we invest into pushing against friction ends up being lost. It's not energy that's retained. Frictional forces dissipate energy as heat, it turns out. When you have conservative forces, the energy that you use to push against that force ends up being kind of stored in the force field. You can get that energy back as long as you move your position back to where it was when you started. So if I have two charges and I have to push with some force to separate them from each other, I put more energy in, but then if I allow those charges to come back and approach each other, I get that energy back. So there are conservative forces and there are non-conservative forces. In this class, a lot of the models that we'll be looking at, we're going to assume that there's no non-conservative work done, and the energy changes that we use are going to be against conservative forces. And so when we put energy into something, it's going to be stored in the field and we'll get it back. We'll basically be looking at electric forces and these pressure volume expansions. For right now, this is the guy that is the most important to us, because we're going to be looking at the ideal gas model, or gases in general, and we'll look at the work that they do as they expand and contract. So again, the expansion work ends up being the integral of P external dV. Is that all that I had to say about that? And that was just a slide that we showed last week. These are some of the different kinds of work that can be done against conservative forces. So, well, mechanical work isn't necessarily conservative forces, but against a surface tension or against a potential difference or against a gravitational force or expansion, all of these guys are conservative forces. Mechanical work doesn't necessarily have to be conservative. If it's done against friction, the heat gets dissipated. So again, with heat capacities, the heat capacity is a measure of how much heat is required to change the temperature of an object by a certain amount. And when we think about heat capacities, I want to go back to that analogy that we used where temperature is some kind of a pool, and our system is immersed in that pool. And our system has different kind of, in the analogy, if our system is a porous rock, it has different places that energy can spill into. And some of those pores are higher in energy than others, and so they don't, the bath doesn't spill into them until the temperature or the level of the liquid is raised high. So if the liquid is temperature, before you can populate a state, you have to bring the temperature up to the appropriate level. And so you can think of the temperature of an object as being a measure of how many different energy states are populated, how many of its available energy states are populated. For the system that we are looking at, that we'll be concerning ourselves with the most, the ideal gas, we only have translational kinetic energy that we're allowed to store energy in. We only have what's called 3 degrees of freedom. So we can move in the X and the Y and the Z direction, and we're only allowed to store energy in that form. Real systems have multiple different degrees of freedom that they're allowed to store energy in. We looked at those. We looked at vibration and rotation and potential energies associated with charges, positions with respect to one another. So if we're trying to I will say this. So if we're looking at an ideal gas, the only mechanism that we have for storing that energy is in the translational degrees of freedom, and that the fact that we only have those degrees of freedom available to us leads to a predictable heat capacity for that gas. There's a I don't know if it's a law or a theorem, but a result of statistical mechanics is that certain degrees of freedom impart to a substance the ability to store a predictable amount of energy. And it turns out that for each translational degree of freedom, a system is able to store 1/2 kBt energy. And so if we are looking at the ideal gas model where we only have 3 translational degrees of freedom, our total amount of energy stored is going to be 3 times that, which is equal to 3/2 kBt. So we're allowed to store 1/2 kBt for each translational degree of freedom that we have. We've got 3 translational degrees of freedom, so that means that theoretically the amount of energy that an ideal gas can store in translational motion is going to be 3/2 kBt. This system sorry, I have to thinking about exactly how I want to construct these sentences. This system is able to store 3/2 kBt energy if it had other degrees of freedom available. 3/2 kBt is the heat capacity for an ideal gas that has no ability to rotate or vibrate. If we start adding additional degrees of freedom, for instance, by making this guy a diatomic, and once we have a diatomic, we've got the ability to rotate about an axis, and we might have the ability to vibrate along the bond line, then we introduce new degrees of freedom to the molecule. And for each degree of freedom, we end up having to add a kBt term. I think I needed to do my homework on this and I didn't. I think it's that rotational degrees of freedom allow 1/2 kBt energy for each rotational degree of freedom that's available. And vibrational degrees of freedom add a factor of kBt. Don't quote me on that, I might be wrong. You should go check a source. But the point is that as our molecule becomes more complex, it develops different ways for storing that energy. There's another kind of catch to this, and that is that just because a molecule has a degree of freedom doesn't necessarily mean that energy will be able to be stored in that degree of freedom. There's kind of a minimum amount of energy that has to be available in the ambient in order to activate that degree of freedom. So you might have a diatomic molecule that theoretically could rotate or vibrate, but if your temperature is too low, it won't be able to activate those rotations or vibrations. And so what happens is that you'll see that with certain molecules, the heat capacity or its ability to store energy changes as a function of temperature. At lower temperatures, you might only be able to activate these translational degrees of freedom. But then as the temperature rises, maybe a rotational degree of freedom becomes available. And when that rotational degree of freedom becomes available, the amount of energy that you can dump into that system changes. And so its heat capacity changes. Go ahead.
Oh, so you're saying like the more complex something is, the higher the heat capacity because it has more degrees of freedom?
The more complex it is, the more degrees of freedom it theoretically has. But a lot of those degrees of freedom don't get activated until you bring the temperature up to a certain level. And until the temperature is brought to that level, you're not able to store energy in that system via that degree of freedom. As a consequence of that, that's back to our analogy. You might have some amount of energy that you're able to store. Pretend that this represents translation at some temperature. And translational degrees of freedom are continuous, so it's almost kind of the amount of energy that you're able to store in translation is a constant function of temperature. So we can put those little dots in all over our porous rock. And so the heat capacity would be constant as we move through this temperature range, the temperature being the level of that fluid. If a new degree of freedom were made available as the temperature rose, then we would start to have more pores in our rock that we could fill with liquid or energy or whatever it is we're talking about. So as these new degrees of freedom become available, we can start dumping more energy in. Vibration ends up being higher in energy. We need more energy to excite vibration. So you can imagine that as temperature went up, if a molecule was a diatomic and it had vibrational degrees of freedom available, we'd start getting even more of these guys, more pockets for storing energy. So as a consequence of that, the heat capacity, or the amount of energy that we need to dump into a system in order to raise its temperature, becomes a function of the temperature, right? Your heat capacity changes. It's some constant when you're only activating translational degrees of freedom, but then as temperature rises and you begin to be able to activate rotational and vibrational degrees of freedom, the heat capacity increases because all of a sudden we have more ways that we can store energy in that system. So heat capacity is a measure of the differential amount of energy for a differential increase in temperature. When you read that, think back to this analogy where the heat capacity is a function of what degrees of freedom we have that we can activate the system. Heat capacity is not only a function of the amount of energy that we get to actually store as internal energy in the system. All of these little modes of, or degrees of freedom that we've populated here represent an increase in internal energy of the system. We said that as a system expands and contracts, it does work. And so depending on how much work the system is doing as it expands or contracts, the heat capacity will change. And so we have a couple of different heat capacities. We have a heat capacity that's relevant if we are at constant volume conditions, where we are not allowed to do expansion and contraction work. And we have a heat capacity that's relevant if we're at constant pressure conditions, where expansion and contraction work becomes important. So remember this, we're going to get back to this as we go into, what is that stuff called? Enthalpy, as we start to talk about enthalpy. So we just looked at this and we said that in general, the heat capacity is a function of the temperature. Because at different temperatures, we have different degrees of freedom available. That said, when you guys took Gen Chem and you were looking at heat capacities and you looked at the heat capacity of liquid water, the heat capacity of solid water and gas phase water, etc., that heat capacity it was a constant, it wasn't a function of temperature, right? The key there is that we're looking at the heat capacity in kind of a small range of temperatures, where the degrees of freedom that are available don't change. And so if we're looking at a small range of temperatures for a system, the heat capacity will be a constant, simply because we're not introducing any new degrees of freedom as that temperature changes. So heat capacity in general is going to be the integral, or the heat, sorry, is going to be the integral of the heat capacity times the temperature, and the heat capacity will be a function of temperature, and so you'll have to include that function when you do the integral. For small ranges of temperature, that becomes a constant, and it can be pulled out of the integral, and so the heat change is just the integral of dt, so it'll be the heat capacity times the final temperature minus the initial temperature, right? So we're looking at these constant volume and constant pressure heat capacities right now, and we're just talking a little bit more about those. We can derive relationships between the changes in the internal energy and changes in temperature using the fact that heat capacity is a function of how much energy is dumped into a system under specific conditions. Here, we're looking at constant volume conditions, and under constant volume conditions, the first law tells us that any change in the energy is equal to Q plus W, and so the heat associated with a constant volume process is just going to be, there's no work essentially in a constant volume process, so the heat is just going to be the integral of CV dt. And all of that heat goes to changing the internal energy of the system because we're populating those degrees of freedom. And so you can also say that the differential change in the internal energy is equal to CV dt. Pull that dt under there and acknowledge that you're under constant volume conditions by putting that V down here, and we get this relationship that CV, the constant volume heat capacity, is equal to the partial differential of the internal energy with respect to temperature at constant volume. So when I came in here, we looked at state functions, and we said that state functions have the property that their total differential can be expressed as a sum of differentials with respect to certain variables while the other variables are held constant. Well, what we just generated is a term that tells us what the partial differential is of the internal energy with respect to temperature while volume is held constant, and that is the CV term. So our constant volume heat capacity represents one term in that total differential of the internal energy with respect to temperature. And we'll look at the other terms later. We can measure constant volume heat capacity. It's not too hard. All we have to do is take a material and throw it into a calorimeter, a bomb calorimeter that has volume conditions that don't change, and we essentially inject into that material a known amount of energy, and we measure the temperature change, and that gives us the change in internal energy with respect to temperature, and through that we can acquire a term for CV. So it's not difficult to determine the constant volume heat capacity for materials. All we need really is a bomb calorimeter. Last week we said that for an ideal gas, the internal energy was only a function of temperature, right? And we referenced the work that we've done in the first week, where we did that little derivation using the change in momentum as molecules hit the sides of the container, and we'd come up with the conclusion, we'd come to the conclusion that the kinetic energy was equal to 3/2 kBt. So that equation tells us that kinetic energy is only a function of temperature for that system. Referencing the conversation we had earlier today, where we decided that 1/2 kBt energy is available to each translational degree of freedom, we now see why the the ideal gas has a kinetic energy of 3/2 kBt that's only a function of temperature. That is a consequence of the fact that we only have 3 degrees of freedom. If we had additional degrees of freedom, this would not be true. So let's look at the effect of that. Internal energy is a state function. We can write out its total differential as the sum of partial derivatives with respect to different variables while holding the other variables constant. Internal energy can be expressed as a function of temperature and volume. So the total differential in the internal energy is the partial of the internal energy with respect to temperature at constant volume times the change in volume, plus the partial of the internal energy with respect to, partial with respect to temperature times change in temperature, plus the partial with respect to volume times the change in volume. We decided that our partial with respect to temperature at constant volume was CV. So we have this total differential that says that du is CV dt plus this other term here. This other term is the partial of the internal energy with respect to volume at constant temperature. And again, we said that ideal gases, the internal energy is only a function of temperature, and so that would imply that this term doesn't matter for ideal gases. Well, it turns out that this term, partial of the internal energy with respect to volume at constant temperature, is the term that accounts for another degree of freedom that ideal gases don't have. And that degree of freedom is the ability to store energy in a potential energy due to the attractive forces between molecules. If we have the ability to store energy in the form of that potential, then we introduce another degree of freedom to our system, and that degree of freedom has to be accounted for. So because an ideal gas doesn't have attractive forces between molecules, we don't have that degree of freedom, and so this portion of the differential ends up going away. And so we come to the conclusion that the total differential for an ideal gas ends up being, or the total change in internal energy for an ideal gas ends up being just a function of that CV dt. This becomes important when you do your expansion problems. We'll see one in a second, where you move an ideal gas through, from one state to another state, and you want to quantify what the change in the internal energy is. You end up being able to use just that integral of CV dt for any ideal gas to give you the change in internal energy for any ideal gas as a function of that temperature change. So let's stop right now. There's a relationship. This is this term partial U with respect to V. It's called the internal pressure. Once you introduce the concept of entropy, you can derive this relationship that says that this term is equal to this T times the partial of the pressure with respect to temperature at constant volume minus P. What I want you to do right now is to grab a piece of paper and sit down and evaluate this term for an ideal gas. So tell me what this is equal to for an ideal gas. Remember, for ideal gases, PV is equal to N on T.